Welcome to the data preparation for machine learning demo. In this demo, I will show you how to use Trifacta to execute several common transformations to cleanse and shape your data and perform feature engineering. Let's dive right in. We will wrangle a bank marketing dataset from the University of California Irvine's machine learning repository. This dataset contains information from the direct marketing campaign of a Portuguese banking institution. We will prepare this data to train a machine learning model that will predict whether or not a given client will subscribe to a term deposit. The data comes to us in the form of a CSV file. I will now click on Add Recipe, then go to the Edit Recipe to wrangle it. Trifacta opens the dataset in a familiar Excel-like view where I can explore the data. Notice that Trifacta provides a value histogram for each field, which lets me get a quick overview of how data in each field is distributed. There is also a data quality bar that alerts me to any missing or mismatched data. This data contains several categorical variables. For example, the job field contains 12 discrete values. Before I feed this to a machine learning model, I need to convert these to a numeric format. This process is called one-hot encoding. When I select the job column, I am presented with a number of suggestions. I will pick the values to column option. This creates individual columns for each job type and puts a binary 0 or 1 in the value. Notice that Trifacta provides a live preview for each transformation. This looks good, so I can confidently add this step to my recipe. Next, I will work on the age field. In this case, we will convert a range of continuous age values into discrete bins. For this, I will use the bin column transform. I will choose age as the column I will apply binning to. I could create equal sized bins, but in this case I want to create custom bins. So I will go ahead and specify the upper threshold for each bin. The first bin has an upper threshold of 17 to capture all minors. Subsequent bins capture people in their 20s, 30s, 40s, and so on. Everyone age 70 and above belongs to a senior category. Now that I have created age bins, I no longer need the original age field, so I will delete it. Let's look at an example of how to integerize a categorical variable. The dataset contains an education field that contains a text representation of the level of educational accomplishment. I will create a calculated column based on it. In this case, we use a case statement to associate each educational level, starting with 0 and going up to 7 for a university degree. I will now scroll to the last column of the dataset. This contains the target variable, which indicates whether or not each marketing action resulted in a subscription to a term deposit. As you can see, most of the records represent no, and there are relatively few yes records. This is an example of an unbalanced dataset. While this is a very common situation, it is often useful to have a balanced dataset to train the model to recognize all classes effectively. To begin balancing this dataset, we will first create an ordered row number field that sorts the dataset based on the target variable and derives a row number. We will use the rolling sum function to increment the row number. This is a window function that requires you to specify the sort order. We will choose to sort the data based on -y, which indicates descending order of the target variable y. Next, we will count the occurrences where the target variable equals yes. We create a new formula-driven field named records to keep, which is calculated using the countif function. We multiply this by 2 so that we get an equal number of yes and no records. Notice that this results in a value of 9280. We will then filter the dataset based on the ordered row number field. We will choose less than or equal to, then choose records to keep as the comparison column. After we apply this recipe step, notice that the dataset now contains 9280 rows with an equal number of yes and no values in the target variable. We will now split this dataset into a training and test dataset. To do this, I will create a calculated column based on a random number. Then I will edit this column and apply an if condition. If the random value is less than or equal to 0.8, I will assign a training label, otherwise give it a test label. This will result in approximately 80% of the records to be assigned to the training dataset. Before I produce the datasets for training and testing, I will remove some unnecessary columns from my dataset. To do this, I simply select the columns I want to delete and choose the delete suggestion. I will now go back to the flow view and create two new recipes based on the result I have so far. I will call these recipes training and test. We can edit the training recipe to filter on only those rows where the dataset equals training. Next, we do the same thing for the test recipe. Finally, we go back to the flow view to create an output for model training. We choose the Run Job button. Here we choose the running environment, which in this case is Trifacta server. For larger jobs, you can leverage the scalability provided by a Hadoop cluster. You also choose the publishing format. The default is CSV, but I can add additional publishing actions and choose from Avro, CSV, JSON, Parquet, and TDE as the output formats. Now I click on Run Job. Once the job execution is complete, we can view a detailed profile of the results. If this looks good, we can proceed to export results. These results can then be used to train your machine learning models. I hope this video gave you an overview of the common data preparation steps for machine learning. We barely scratched the surface here, and there are a lot more features in Trifacta to simplify data prep for machine learning. Hope you found this video helpful, and if so, please be sure to like and share it or post a comment below. Thank you.